In this lesson, we continue our study of probability, and we're going to formalize all of the rules that we have learned so far, as well as learn more general versions of them. So the first rule, which you've already been using a lot, is the complement rule. So if you know an event A occurs, you can use the formula P of A complement equals 1 minus P of A to find the probability that A does not occur. And remember, that comes from the fact that P of A plus P of A complement has to equal 1, because A and A complement together contain all the events in your sample space and nothing in common. So solving for a probability of A complement, your probability A complement is 1 minus P of A. A fair coin is tossed 3 times. The event A is getting all heads and has probability 1/8. Describe in words what the event A complement is. So A complement is not getting heads in all 3 tosses. Or a more clear way to explain this might be that A complement is having at least 1 coin come up tails. And what is the probability of A complement? Well, P of A complement is 1 minus P of A, and we know that the probability of A is 1/8. So the probability of A complement is 7/8. Assuming that all 365 days are equally likely, what is the probability that a stranger does not share your birthday? Well, the probability that you share a birthday, assuming no leap years, is 1 out of 365. So the probability of not sharing, which is the complement of sharing, is 1 minus the probability that you share, or 1 minus 1 over 365, or 364. Out of 365. Next, we have a rule for ORs, which is the probability that either one or both of these 2 events happen. So one important thing to note is that mathematically OR means A or B, but both is also a legitimate possibility. So the general rule says that you're finding the probability of A or B. You find P of A plus P of B minus P of A and B. And rule 2b applies for mutually exclusive events, and we've already used this rule, that P of A or B is P of A plus P of B. So question 1 is, do we really need 2 rules? And the answer is no. If A and B are mutually exclusive, they contain none of the same simple events, and so this makes P of A plus P of B minus P of A and B. Because A and B contain none of the same simple events, there's nothing in A and B, so this thing is 0. And that's where they get the P of A plus P of B thing, if we have mutual exclusivity. Now, another reasonable question to ask is, why is there this term where you take away P of A and B? And that can be explained with a little Venn diagram. So suppose we have A and we have B. Now think P of A counts all that stuff. P of B counts all of this stuff. So if you just compute P of A and P of B, and if your events have overlap, this little bit in the middle, which is called the intersection, that little bit's been counted twice. And that's why you have to take away one of those intersections. Okay, suppose that people are equally likely to have been born on any day of the week. You meet a new friend and ask her on what day of the week she was born. So first, list the simple events in the sample space. Well, the simple events are just going to be the days of the week. So our sample space S is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So there are 7 simple events there. What is the probability that she was born on a weekend? So that's probability of Saturday or Sunday. And those are technically mutually exclusive events. So that's probability of being born on Saturday plus probability of being born on Sunday. And each of those occurs with probability 1/7. So Brett is off to college. There are 1,000 additional male students, and one of them will be randomly assigned to share Brett's dorm room. He's hoping that it won't be somebody who likes to party or who snores. So use the following table to find the probability that Brett will be assigned a roommate who either snores, likes to party, or both. So let's let A equal the event that the roommate likes to party, and B equal the event that the roommate snores. Well, the probability of A or B, we don't know if these events are mutually exclusive, so let's just assume that they're not, is equal to P of A plus P of B minus P of A and B. Okay, so first of all, probability of A. How many people like to party? Well, there's likes to party right there. 250 total students like to party. So 250 out of 1,000. Probability of snores. Well, there's that many snores, 350. Minus the people who do both. Well, that's this entry in the table here. The likes to party intersects with snores. 150 people there out of 1,000. So that's 0.25 plus 0.35 minus 0.15, which works out to be 0.45. So there's a relatively, almost 50-50 chance that he's going to have a roommate who either snores or likes to party. Okay, next we're going to talk about a probability rule for ands. So the probability that A and B occurs. So one way to find probability of A and B, the most general rule, is that to use those conditional probabilities from last time. So the probability of A and B is either P of A and then times probability of P of B knowing A happens, or P of B times P of A given B. And which of these rules you use would depend on which conditional probability you had. Okay, and if we have independent events, then this thing would end up equaling P of B because the knowledge of A doesn't change B's probability, and this would end up equaling P of A, and that's what gives us this next rule. but that's only true if those events are independent. And one kind of useful extension is if you have lots of independent events, the probability of the first and the second and the third, you can just generalize Rule 3b and multiply each individual probability. Usually independence is an assumption that's made so that you can use this rule, but you should just be careful because events are not always independent. Okay, a brand of cereal boxes contains a prize in each box. There are 5 possible prizes, and each of the prizes is equally likely to be in any box. So if you purchase 2 boxes, what is the probability that you receive the same prize in both boxes? So first of all, let's find the total number of sort of prize combinations. So how many choices for the first box prizes? Well, there can be 5 different things in there, times 5 choices for the second, for a total of 25 different prize combinations. And then the ones that are the same, well, if we number the prizes 1 to 5, we could have prize 1 and prize 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, for a total of 5 events there. So the probability that we have the same prizes in all boxes is 5 out of 25, which reduces to a fifth. So if you've purchased 2 boxes, what's the probability that you receive 2 different prizes? Well, it's the complement rule here. Probability of not the same will be 1 minus the probability that the prizes are the same. So 1 minus 1/5 or 4/5. All right, Julie is taking English and history. And suppose at the outset of the term, her probabilities for getting A's are as follows: A in English, 0.7, A in history, 0.6, and an A in both, 0.5. So we want to figure out are the grades of A in English class and grade of A in history class independent? Explain how you know. Well, let's let E be A in English and H be getting an A in history, just to shorten up our writing. So we'll check using the rule for ands. P of E and H. The probability of A in both classes is 0.5. And these events are independent if and only if this equals P of E times P of H. And since we know those individual probabilities, we can figure this out. So probability of an A in English is 0.7. History is 0.6, which is 0.42. And as P of E and H is not equal to P of E, P of H, these events are not independent. i.e. they are dependent. Next, a really reasonable question is, what is the probability that Julie will get at least 1 A between her English and history classes, meaning A in English or A in history, or possibly both? So the probability of E or H, and this problem tells you what rule to use, but in general you'll have to figure out that this is what you have to use yourself, would equal P of E plus P of H minus P of E and H. Don't forget this last part because that matters. The probability of an A in English is 0.7. Probability of A in history is 0.6. And the probability of A's in both classes is 0.5. So that works out to be 0.8. Sometimes application of the complement rule can be a bit tricky, and they can be paired with that formula which generalizes many independent events happening in succession. So here's an example of that. So suppose at a high school in a small town, it always has its homecoming day and parade on the first Saturday in October. And from historical records, it has been determined that the probability of rain during the parade is 0.15. Suppose you go to this high school. What is the probability that it will not rain on the homecoming parade during your freshman year? Well, that's pretty easy. That's just the complement rule. Probability of not rain is 1 minus the probability that it rains, or 1 minus 0.15, or 0.85. So what is the probability that it will not rain for any of the homecoming parades during your 4 years at school? And you have to assume that from 1 year to the next is independent. So let's let R equal rain, in which case our complement is no rain. So we want the probability of no rain and no rain and no rain and no rain, like no raining 4 times. You see how this is 1, 2, 3, 4 independent events. So that is this rule 3b extension, which tells you this is equal to probability of no rain times probability of no rain, etc. 4 times. And each of those has probability 0.85, so what we really have here is 0.85 multiplied by itself 4 times, or 0.85 to the 4th power, which works out to be 0.552, or no, excuse me, 522. Okay, now here's where the tricky complementing comes in. What is the probability that it will rain at least once during your 4 years of attendance? So first of all, at least once means it rains 1, 2, 3, or all 4 times. That's what it means to rain at least once. And the thing to notice is that is the complement of part B. The probability of rain at least once is 1 minus the probability that it never rains. And you can think about that as in it can rain 1, 2, 3, or 4 times, or it could rain no times. We found this in part B, and those 2 events definitely cover the sample space. And that's pretty helpful because it could rain once in 1 of 4 ways, either your 1st year, 2nd year, 3rd year, or 4th year. It could rain twice in a whole bunch of different ways, 3 times in a bunch of different ways, as well as 4 times. Well, that can only happen one way. But you have to find the probability of each of those individually, and that would be really cumbersome. It's much easier to use this complementing thing. So this is 1 minus our answer from part B, which was 0.522, which works out to be 0.478. So just a little vocabulary rule. A sample is drawn with replacement if the sampled individuals are returned to the eligible pool before each selection. And a sample is drawn without replacement if the sampled individuals are not returned or not eligible for subsequent selection. So in each situation, explain whether the selection is made with replacement or without replacement. 5 people are selected for extra security screening while boarding a particular flight. So this would be made with replacement if somebody selected for extra security training could be selected again. And I think in general, that's not how this works. This is probably something that works without replacement. Now, 3 digits in the lottery. Now, I bet this can vary from lottery to lottery, but I think we're just going to, for the sake of this, assume that this can happen with replacement. Probably. Numbers can usually be drawn again. Okay, determining a conditional probability, so rule number 4. This is a restatement of rule 3a, but it's a bit more useful in this form. So what rule 3a said was this. Rule 3a said that P of A and B was equal to P of A times P of B given A. And it also said that probability of A and B was equal to P of B times P of A given B. And what you can see happened is, in this first thing, if you divide by the probability of A on both sides, that gives you probability of B given A equals P of A and B over P of A. And with this one, if you divide by probability of B, you get probability of A given B is P of A and B all over P of B. And the way I remember this rule, whether or not it's helpful to you, but it's helpful to me, is that the thing that you're given is the probability that goes in the denominator. So if you're finding B given A, you divide out P of A. If you're finding A given B, you divide out P of B. And the reason that A and B don't switch is that the probability of A and B is the same as the probability of B and A. So that's why the numerator stays the same, because those two probabilities are equal. All right, let's use this to solve some problems. So this one, I'd like to use that rule, but technically speaking, you don't actually really need to. You can just reason your way through this. Suppose in a class of 50 students, three students are asked to answer a question, and suppose that one student is Constantine. What is the probability that Constantine is asked to answer the first question, given that he is chosen to answer? So let's just state what this is based on sort of a little bit of logic, and then let's use those rules to figure it out. So A is going to equal chosen to answer, and B is going to be he's chosen first. So we're finding the probability of B given A. Well, if he's chosen to answer, he's one of these 3 people, so he has a 1 in 3 chance of being chosen first. So if you can do this that way, that is totally the correct answer, you're fine, you're done. But let's just talk about how the rule we just discussed could apply here as well. So P of B given A is the probability of A and B over probability of A. The probability of A and B is that he's chosen to answer and he's chosen first. Well, only one person out of all those 50 people is chosen to answer and is first. So that happens with 1 out of 50 probability. And P of A, the probability he's chosen to answer a question, well, there are 3 students chosen out of 50 total. Multiplying my numerator and denominator by 50 here, I end up with 1/3 as well. But like I said, you can do that problem just without this rule at all because it's pretty easy to reason through. So in a recent election, 60% of the voters were Republicans and 40% were not. Of the Republicans, 90% voted for candidate X, and of the non-Republicans, 30 voted for candidate X. Consider a randomly selected voter. Let A be the event that the voter is Republican, and B be the event that they voted for candidate X. Find the following and describe what they mean. All right, so probability of B given A is equal to probability that they voted for X given Republican. So if we know they're Republican, what's the probability that they voted for candidate X? Well, that's just told to us. That's 90%, so 0.9. This is the probability that they voted for X given not Republican. And we're given that as well, which is 0.3. And the probability of A and B, what's the probability that you are Republican and voted for X. And we can use rule 3a to figure this out. This is equal to P of A times P of B given A. Well, the probability that you are Republican is 0.6. And the probability that you voted for X given that you're Republican was 0.9. So in the general pool of things, the probability that you were Republican and voted for candidate X was 0.54. So suppose that 4.9% of property crimes occur in rural areas, and 1.9% of these property crimes are in rural areas and are burglaries. So we want to figure out what proportion of property crimes that are in rural areas are burglaries. So it might be the case that property crimes are more common in rural, as in burglaries are more common in rural areas than elsewhere. Maybe other crimes are more common in big cities. So first, let's start by defining some events. We have talking about a rural place, so let's let R equal the event where we have a property crime in a rural area. And let's let B be the event that we have a burglary. What percent of property crimes that are in rural areas are burglaries? So what we really want is the probability of a burglary given you're in a rural area. So knowing you're in this rural area, what's the probability that we're going to have a burglary? Well, that's the probability that you have a burglary and you're in a rural area, divided by the probability that you were in the rural area in the first place. And then we're given those numbers. The probability of having a burglary and being in a rural area was 1.9% or 0.019. And then the probability that you're in a rural area was 0.049, which works out to be 0.387. So if you're in a rural area, about 38.7% of the crimes that occur are burglaries. So suppose the probability of winning a particular casino game is 0.2 and is independent from one game to the next. If someone plays the game 4 times, what's the probability of winning at least once? So, well, the thing is, if you're going to win at least once, so to win at least once means you win 1, 2, 3, or all 4 games. And so you'd figure out, okay, what's the chances you'd win 1 game? What's the chances you'd win 2 games, 3 games, and 4 games? And that's complicated. So the thing to observe here is that this is the complement of never winning on all 4. So for 1 game, your probability of losing is 0.8. Probability of losing all 4 will be this 0.8 to the 4th, which comes out to be about 0.4096. So the probability that you will win at least 1 is 1 minus the probability that you lose all 4, which is 1 minus 0.4096, or 0.5904. But the tricky thing there is you have to recognize that this is both an application of the complement rule and the application of the generalized rule for events of and with independence. That's where this 0.8 to the 4th is. Really, we find the probability you lose on round 1, lose on round 2, lose on round 3, and lose on round 4. So suppose in a dorm room, the probability that there is a TV is 0.52, and the probability that there's a mini fridge is 0.38, and the probability of both is 0.21. So find the probability of no TV in a randomly selected dorm room. Well, no TV would equal 1 minus P that there is a TV, 1 minus 0.52, or 0.48. So what is the probability of having a TV, fridge, or both in a randomly selected dorm room? So that's the probability of, we'll say, T for TV or F for fridge. Well, for that we use our rules for ORs, which is P of T plus P of F minus P of T and F. And don't forget that last part, because unless the events are mutually exclusive, that thing is going to be non-zero. So the probability of a TV's presence is 0.52. Probability of a fridge is 0.38. Probability of both is 0.21. So this works out to be 0.69. What is the probability that there is a TV given that there is a fridge? How about a fridge given that there is a TV? So probability of TV knowing there is a fridge. Well, that's what we're calling rule number 4. Probability of TV and fridge divided by probability of fridge. So that's 0.21 divided by the probability that there's a mini fridge, which is 0.38. And that works out to be approximately 0.55. And the other one, probability of fridge given TV, almost the same, probability of fridge and TV over probability of TV. Well, fridge and TV is the same as TV and fridge, so that's, again, 0.21. Probability of TV was 0.52, which works out to be 0.404. And that should kind of make sense that knowing that one event occurs, as in the fridge is there or the TV is there, probably increases the chance that that roommate just has everything and they have the other thing as well. In the first case, the TV, in the second case, the fridge.